Okay, so welcome everyone. Thanks all for being here. And so today it's our great pleasure to have Eveliina Peltola, who will be telling us about large deviation of SLEs, real rational function, and determinants of Laplacians.
Thanks a lot. I'm very happy to speak and see all these friends again. It's been a while when we saw in person. So at least this way we can have some seminars. So as I was lazy, the title here is just the title of the paper. That's why it's quite long. So I'm gonna explain all this stuff. Don't worry, you don't have to know any of these things beforehand. And feel free to interrupt me anytime. This is based on work from, well, last year, relatively recent, with Yilin, who might be here as well, who's at MIT. And yeah, so the goal is to explain, well, SLEs, most of you maybe know, but I'll still tell you what they are. Then explain a main result about large deviations of those. And I hope to give some connections to rational functions, which is quite cute. And also connection to determinants of Laplacians, which are not so surprising from the physics point of view, but somehow maybe from the original problem, not so clear. So let's see how to start like that. So I made some list of things I'd like to talk about, and we'll see how far I can get. So for me, maybe a little bit personally, motivation to study all these conformal invariant things comes from statistical physics in the plane. So that's somehow what one wants to understand in the scaling limit, especially the critical models, which should be related to the CFT, stuff like that. And in particular, you find this conformal structure that comes in the plane. Everything I will speak about is in 2 dimensions. Sometimes you could think about some Riemannian surface, but let's just be in the complex plane or Riemann sphere. And so one kind of geometric approach to understand these statistical physics models is study interfaces between various types of atoms. So there will be pictures in the next slide. This first one has a lot of text, so don't worry. So then you encounter these SLE curves. So they have their name from Schramm, who introduced them as random curves, and from Schramm-Loewner, who studied analogous things in the deterministic setup already in the 20s, yeah, almost 100 years ago. So I'm gonna say SLE because it's much shorter. And they are somehow canonical objects for random planar curves, which are in some sense encoded into Brown motion. So quite universal. And in particular, you see this conformal invariance, which is sought for in these models of interest. So they were a very successful candidate to understand at least interfaces in the critical models in some geometric way. And so then what the topic of today really is a certain type of limit of this. So there's a parameter, which I didn't write here, it's called kappa usually. And the parameter is going to go to 0 from the right. That's like some kind of classical limit. There's a lot of cheating and quotation marks because somehow I'm trying to describe intuition, but for example, meaning of what is a semiclassical limit. It's not clear, so just an idea. And so then what happens is that the random curves, the SLE curves, they concentrate on some deterministic curves. And then there's a rate function, which is, we call it energy or potential. It's a functional on curves. And that is a very interesting object, actually, that was discovered already earlier by Yilin, and we kind of elaborated on this by introducing a certain quantity called the potential, which seemed to be actually more fundamental in some sense, at least encoding more information. And you can write the formula for this guy in terms of these determinants of Laplacians. So, well, after regularization. So that's how this one phrase in the title comes into play. And finally, if I get there, in the end, I will try to remark some connections. So here are a few connections of these objects to other seemingly unrelated areas. So to real enumerative geometry, for example, to maybe to interest to the audience are semiclassical conformal blocks. But in my case, my CFT will be C less than 1, so it's not the Liouville, but the matter fields. But I think from Liouville, you get the same kind of things actually in this kind of limit. So it's not so far from each other. And there are some integrable systems also related, as is discussed by this preprint of Albertskan and Makarov, also from last year. And probably other things I forgot. So there's a lot of seems to be a lot of connections to other things, which is maybe the most interesting part of the result. So this is the main result that I will present, and this is just some additional stuff. All right, so after a lot of text, let's go to a bit more concrete things. And start from some pictures from motivation. So for those of you who haven't heard about SLEs, so what are they and how can you think about them? So one way to kind of arrive why these SLE curves would be interesting is to try to study some statistical physics models. So models that describe some material, for example, magnetism, magnetic properties, or porous material like percolation, or some other things, maybe spreading of disease, something like that. And common to them is that they have lots of objects, so atoms or particles or whatever. So then what you just look at the properties on average. And that's why you have a statistical model. And certain types of these models, which are called critical, they are expected to have in the continuum limit, so scaling limit, which means you model your objects in a grid. So like here, you take the mesh size of the grid to 0, and then you encounter kind of like a continuum domain, continuum model. That should be described by quantum field theory in the physics point of view. And for these critical models, what is remarkable is that there's an additional symmetry under conformal transformations, and that's something that mathematicians have been trying to elaborate on. So, for example, how to make this limit precise and how to see this conformal symmetry. So these have been quite vivid topics of research in the last, I don't know, mathematics community, maybe 20, 25 years. In the physics community, much earlier already. And how to get to my problem, which is here. Let's look at the interfaces in the pictures. So the pictures are small, but hope you can see two colors, and then you can separate the colors by some macroscopic interfaces. And I've put some boundary conditions for the models to impose this kind of appearance of macroscopic interfaces in certain positions. And they are quite fractal looking, like here, right? So after taking the scaling limit, they are described by these SLE curves. And now there's a parameter that I've been hiding, which is related to the model. So in this picture, the parameter is 3. Here it's 6. I don't think I have other pictures. It's always positive. And the point is that when you take the parameter to 0, you can, in some sense, view this as some kind of semi-classical limit, which for us means just that the fractal curves, they concentrate on some kind of optimal curves. Like in this picture, the optimal curves are these kind of quite smooth looking ones, the green ones, and then there's some fluctuations, and you want to make this precise in terms of large deviation principle. And that's what you can do. Then for this limit, there's not really a model from physics, corresponding to it, but it's rather some kind of limit, maybe more in this CFT perspective. All right. So then let me show a little bit, in case you've never seen it before, just a bigger picture. So you can think about what I'm going to talk about are interfaces connecting some boundary points of some domain. So here's an example. And one natural way where you see them are these physical models. So here I have 4 interfaces. You see I have put some boundary conditions here, black on those segments, and then blue on the other segments, and inside it's random. And then you find this kind of configuration. So this is the simulation of the critical easing model. So I'm going to talk about critical models, although I usually omit that in the slides. I'm actually cheating a lot, so please interrupt me if something is confusing. So let me show a slide about the easing model phase transition, just for those who haven't heard. So what is the model? It has spins, which have 2 colors, so plus minus 1, so these are the 2 colors. And this middle picture is what I'm interested in. It's called the critical. And there's a temperature in the model, which can be varying. And you see that, so this is a low temperature case. And the kind of typical configuration looks like this. So it's quite ordered. There's one half is one color, the other half is the other color. In high temperature, you see very disordered region, really white noise kind of thing. And in the middle, something interesting happens. So this is called the critical temperature. And the temperature, it appears in the intrinsically in the model. So look at configurations of these spins, plus minus 1 at vertices. You have some interaction between, this is nearest neighbors. And then there's the temperature parameter here. So the details is not so important. The picture is useful to keep in mind. And so this kind of phenomenon, when you vary the temperature or some other parameter, it's called phase transition in any statistical physics model. And by randomization group arguments, if you look at this critical case, you actually expect some conformal variance. You expect some conformal field theory to be somehow describing that model. But let's not go more into that. Just want to say that what we are considering is kind of some kind of semi-classical limit of this kind of theories in quotation marks. Okay.
Could I ask a question quickly?
Sure.
Yes. So the prediction on TC, this critical temperature, and the prediction on beta, do we have by renormalization group exact characterizations of the temperature and beta?
You mean the number for it?
Yeah, the scaling exponent beta and the critical temperature.
Beta.
Are those predictable?
Yeah, I think it should be 1/8 or 1/4. This is, yeah, maybe randomization group arguments might give it, but there's also some CFT arguments that can be used to predict those. It was done quite extensively by Nienhuis in the 80s. Fortunately, this doesn't stick. yeah, there are some predictions. I maybe should have written here. I always forget if it's 1/8 or 1/4, but anyway.
Yeah, thank you.
Right. And you see, indeed, one way to see the phase transition is look at correlation between two spins in X and Y, somewhere far away apart. And well, in the low temperature region, there's a lot of correlation, nothing very interesting actually. In the high temperature, you have almost decorrelated, so exponential decay. There's some constant here called correlation length. So exponential decay in the distance. And then in the critical region, indeed, there is this critical exponent, which has been predicted in 2D. So in higher dimension, there's no numerical value predicted. Sorry, no algebraic value, but there are some numerics in 3D, actually by physicists quite recently, who have quite precise numerics on these exponents. But in my case, I'm always in 2D. For example, on the square grid or some other grid. So here you see it's a polynomial type of behavior for the correlation of spins at two kind of far away points. So there's really drastic difference of behavior, which is one way to define the phase transition. All right, any more questions? Okay, so then let's jump on. Maybe I jump for the whole thing. So I already mentioned this. So then how to make sense of the scaling limit. So one wants to take this kind of delta times delta squares or some other graph, and then let delta go to 0. So delta is the mesh size, and see what happens, and discover some CST, hopefully. I'm not going to really talk about that, but you can study correlations that was studied, for example, by these people and others. You can study some kind of topological events that also I'm not going to talk about. Maybe I should cross them. What I'm going to talk about are these interfaces. So you can focus on the picture with boundary conditions, one color on one side, one kind of half of the boundary, another color on the other side. So the colors are plus and minus. And then you always have an interface between the two colors, and that's some quite random. It's a random, quite fractal looking curve. And when the mesh size goes to 0, it should converge to some object, which should feature this conformal invariance. So this is in the critical. I'm always in the critical region here from now on. And indeed, that was done. So by these people, initiated by Spino. So here's a little bit rough statement. So this is for the easy model because it's a nice example model. So you see the SLE appearing again. So if you look at this interface, so it's some object in a space of curves connecting these 2 points in the square, let's say. And you take the mesh size to 0. The law of this interface converges weakly to this kind of SLE curve. So I will tell you next what it is. So that's some kind of breakthrough result in this description of these critical models, especially for the easy model case. And SLEs were introduced by Schramm mainly to describe this kind of models. So in that sense, it was a great success. So then what is this SLE? So let me first focus on this one curve case. Then on the other picture, you can have several curves in the same model, somehow with some slight complication, but it's natural anyway. So you see, I reveal it again. It's easier like that. So here's a definition / theorem. So let's see, let's look at chordal curves in some simply connected domain to the simplest case. with two marked boundary points, and the curve is supposed to connect the boundary points. It may touch the boundary of the domain if you want. In my examples, it won't. So it will be a simple curve actually, just between the points. Unparameterized, so just a geometric object. And it should have some natural properties. For us, important is conformal invariance. So if I map my domain to some other domain by a conformal map, and the 2 points will be mapped somewhere, and I can pick where they map, actually, if I want. What is the law of the curve here? So here would be f of gamma. So that would be just the SLE law, but in this new domain. So that is what the conformal invariance is referring to. So I have a law property measure on these objects. And here I'm just pushing it forward. And I say that the push forward doesn't kind of do anything, you just change the domain data. So if you impose that property of number one, number two, a certain Markov property that I'm not going to need, so I'm going to skip it, but it's something analogous to Brownian motion. Then Schramm showed that there's just one parameter family of laws for this kind of Gödel curves, and he called the parameter kappa. And that is somehow related to the fractality of the curve. So that's going to come in the next slide more concretely. So then one way to define SLE kappa is to be a probability measure on Gödel curves like this with these two properties. And then there's still one parameter to fix. But it's a little bit maybe abstract to define like that. But I hope you keep the picture in mind if you haven't seen it before. So you have a random curve connecting two boundary points of a simply connected domain. Of course, you could try to generalize to other setups. Let's just stick to this. And let's see a bit more concretely how to generate these guys. So what is the idea of Schramm? To construct such an object. So he was using or rediscovering some very classical work of Loewner, who was working in the just deterministic setup. So let's now, because we are conformal invariant, let's go to the upper half plane. And let's start from some marked point. And let's say we go to infinity, which is also a boundary point, right? And let's pretend we look at some simple curves, because I'm not going to need anything else. So here's my simple curve. So maybe I want some more concrete description of it. So I pick some parameterization. So now it's parameterized by time. And I say at any time, I can actually map, where does it go? The initial segment of the curve. The complement of that, it's a simply connected domain, because I have a simple curve. I can map it back to the upper half plane by some conformal map, which depends on the time. And that is called the Loewner evolution for this, associated to this curve. And now the future of the curve, which is the dashed stuff, that is just going to be mapped there as well. And for each time I can do this, and hence I can encode the growth of the curve into these conformal maps. So alternatively of the curve, I can just look at conformal maps. And they have some properties that have been studied, so they satisfy certain differential equation in time. And what comes there is there's the map itself at some point set. And then comes an object, which is called the driving function. So what is it? It's just the image of the tip at time t, which always gets mapped to the real line. So when time is varying, this w is just going to be a real valued image of the tip at each time. So I can say it's a function of time, or driving function. So if you do conversely, you see that somehow if you know this w, It should be a subscript here. So then you know how the curve is growing, right? And so now the point is that we can put some random function here. And then these maps will be random. And then the curve will be random. Okay. And so the details are not so important, just a picture. So now if I want to get to my SLE, so it needed to have some natural properties, which should be somehow inherited from the scribing function. So what you do, so if you pick the one-dimensional Brownian motion times some speed, you will actually find conformal invariance comes from somehow scaling property of the Brownian motion immediately. And this Markov property that I skipped, that is coming from the Markov property of Brownian motion. So somehow the most canonical random curve that you can look at in the plane is driven by Brownian motion. But maybe you can still want to vary this somehow the speed, how much is winding. So the bigger the kappa, the more it's winding here. And what we will look at is the limit kappa goes to 0, in which case, you know, this becomes just constant, right? And what happens then is that the curve is just a straight line from 0 to infinity, just the hyperbolic geodesic in the upper half plane. So that is the large deviation limit. Do you have questions on this construction? It was probably known for many of you.
In the chat, there's one question: what is the role of the domain in Schramm's result?
So because we have conformal invariance, the domain doesn't really matter much. So if I have the domain there, to know the law of the curve in this domain, I can just first construct it here. So I map these points to 0 and infinity and to upper half plane. And I construct my guy there. Then I can map back to the domain. And everything gets transformed and pushed forward by this conformal map. And I want to map 0 to this point and infinity to that point. So there's no huge role. If you take multiply connected domains or some other complicated geometries, of course, it's different. So this is really in the simply connected case. All right, so I'm going to talk about the driving process or driving function. So that is just going to be the image of this tip in this construction. So at each time t, I will do that. And I was cheating a bit by not telling you that there's some choice of normalization for this map, because there are many conformal maps from the complement of the curve to the upper plane. So I'm choosing this one in such a way that it looks like the identity near infinity. But again, it's not important to understand what I'm going to talk about. So don't worry, it's just some specific choice, okay? Okay, so then what we have as an input is Brownian motion. And we plug it into Loewner's theorem. So we can actually solve, this if we want. And we will have all this data and we will have our curve, which is the SLE curve. It's actually not clear from this construction a priori that you get the curve gamma, but that was proven by Schramm and Rode in, I think, 2005 or something like that. So we actually get the curve and we can talk about, random curves. All right, and let me say this kappa is kind of small enough that they are simple. For experts, you know what it means. If you don't need to. Okay. All right. So then I want to mention, because I will state the result for any number of curves, that there's a definition also for this case where you want to mark several boundary points and you want to have several SLE curves, which are not independent. So they really describe some phase boundaries of these models. So we call them multiple SLE or multi-chordal SLE in this setup. And just to maybe intuitively, let's still keep our easy model because it's nice. So here's a picture, but now I fixed more points. And I impose some boundary conditions so that I have these curves. And I also decide how they connect. So it's not extremely important here. But of course, from here, there would be also possible that the interface connects to X1, and then these remaining guys in some way. So that's another option for the configuration. And I want to consider them separately, so I just fix one. So that is the data here. And if I do that, I can look at this family of interfaces. So in the picture, I just have 3, or I can have more. Take a certain type of scaling limit, and I will find this multiple SLE. Again, for easy model, it's the same parameter, of course. And somehow the proof strategy is also quite similar, but I need to tell you what this object is. And that is also a player in the upcoming slides. But if you're confused, you can just think about one curve, okay? So you don't need to think about this many curves. I just want to have them also along the way because we will see them. So what is it? We reveal again. So, okay, let's take a simply connected domain with marked points. They are fixed domain data. And look at families of curves. Now there are even number of points, and they are connected pairwise. So from the easy model simulation, maybe it's believable that the curves shouldn't cross each other, and they should connect to different points pairwise. So you can calculate actually how many different connection patterns there might be. So I'll just fix one. I'm going to always call it alpha. It's just meaning the specification of the endpoints of the curves, like in this picture. And now I can define the multiple SLE a little bit abstractly, but this is, I think, actually the most natural definition, as follows. So let's, we look at probability measures on this kind of multi-chordal curves, so families of curves connecting boundary points pairwise and according to certain pattern. And let's say that we condition on all of the curves except one. So we already know these black curves. And what we don't know is the red one over here. So in this situation, the conditional law of the red one, so what should it be if it should describe this easy model interface? Well, by symmetry, it should just be the single SLE curve, but not in the whole domain, but in this shaded gray domain, which is bounded by the other curves that we conditioned over. So the shaded domain here is random. Its boundaries are random. So that's something very natural to expect. And of course, this should hold for any choice of this red curve. So the picture just has one choice. And then I'm claiming that if I impose this property, there's a unique object, which I then can call this multiple SLE. And it's kind of written here. There's some technical assumptions. It's actually a bit old slide, but at least in this range it's been proven. So it's just a stationary measure of a certain Markov chain when you resample these curves somehow one by one, given the others. And it's then a law on these curve families. Okay, so that's what I mean when I say multiple SLE. And if you got confused, just forget about the other curves and just think about one, okay? All right, so then finally, let's get to the main thing, unless you have questions. All right. So now we have our SLE curves with this parameter kappa, which is describing somehow the model. So here kappa is 3 for the easy model. And what I want to study is the limit of the kappa going to 0. So it was always going to be positive. And when it was 0, actually the driving function, it's not here, it was Brownian motion times this speed. So the speed equaling 0 means that the driving function is constant. So actually you have a quite a trivial kind of curve. And when the parameter kappa is positive, you somehow fluctuate near those deterministic curves. And let's try to make it a bit more precise. So now gamma will be my SLE curve, decorated by kappa, which is this parameter. And I can have, any number of them. I have fixed some domain data beforehand, and also how they connect. And now, intuitively, I want to say, so I want to study some reference curve, which is called eta here. And I want to ask how far is gamma from eta? You have to measure it in some way, which in our case is the Hausdorff metric. And when in this large deviation limit, you should see concentration, so of this form. So there's some positive functional of eta here, which is called energy. It's the rate function. Then there's kappa, which is the parameter. And you have a somehow exponentially small probability of staying close to a given curve. And the highest probability is when this energy is smallest, because there's a minus sign. And to maybe show a picture and theorem. So here's the picture. Maybe look at that first. So here again, the red curves are these SLEs fluctuating. And the green curves, you see the color, those are this eta. And then this kind of dashed thing is some neighborhood in a certain sense. So I need to specify a lot of things to make it precise. So topology on the space of curves. We take just somehow in terms of Hausdorff distance. And okay, then to state what this concentration means precisely. So this is the standard large deviation type abstract nonsense statements. But it's kind of what I wrote here. So that is the main theorem. And okay, one line proof. Next slide has a little bit more comments on that. So we know already something for Brownian motion. So there are results like that by Schilder. And that's, of course, the first thing that comes to mind that one wants to use. And before going further, I should say, for one chord, this was studied by Yilin in her thesis. She has actually several papers about it. And she introduced this Loewner energy that I haven't told you what it is yet, for one curve. And she proved a version of this theorem with a certain type of characterization of this property in terms of the curve passing kind of between certain collection of points, which was a little bit artificial, if I may say. So we improved her result, and we include this several curve case in the same time in our work. And this functional was also introduced earlier by Fritsch and Shekhar when they studied Loewner chains in general and regularity. So somehow that is not new, but it's relatively recent. So these are in the few years ago, somehow surprising maybe. And lots of kind of what goes into the proof is technical stuff. Okay. Already the statement is a bit technical. Do you have questions about the statement? There's not. Let me jump the same statement again. Just I listed a little bit more remarks. So how would you go on proving it? Maybe just for one curve. So it was driven by this Brownian motion with speed kappa. So then you want to somehow compare the driver of this SLE curve and the driver of this reference curve. And there's a result by Schilder doing that. But it only works for somehow in the initial segment of the curve. So if you think about them as parameterized, I would be going from time 0. This picture is maybe a little bit silly, time infinity. So Schilder's result, actually it only works for up to some cutoff time. So that's one technical difficulty for those who are interested. So we have some trouble. So anyway, from there, we can then get to the SLE curves and get a property like this, but again, up to some cutoff time. And here is actually some trouble. So the mapping here is not continuous. So we cannot just use the contraction principle. So there's again some identifying the discontinuity points of the map from drivers to curves and stuff like that. But that can be done. Okay, so then we are having everything up to some cutoff time. And after that, we want to take the cutoff time to infinity. And these are some SLE estimates that you have to do. It can be done. And that is then for one curve. And to get to this several curve, like in the picture, probably I won't talk about too much about that. But what you can think about is these multiple curves, multiple SLE, as taking independent SLEs and weighting by some random equal derivative. And if you've done large deviations, you've seen Varadhan's lemma that can be used. If not, don't worry. It's just some technical tool that can be used to get to the multiple curve case. And we need some understanding of this random equal derivatives. But after that, that is basically it for the proof. And yeah, it's only in the preprint. So it's actually a more updated version. So maybe it's more readable now. Any questions? All right. So then something I haven't told you is what is this rate function? So I hope this intuition somehow makes sense. What the large deviation means. There's some, it shouldn't be there. This concentration, but there's some rate function which depends on the reference curves that is appearing, which was called Loewner's energy. And so let's see how it's defined. So that is I, and there's actually we discovered that there's something more intrinsic, which is we started calling Loewner potential, we call it H. So I will talk about both of them, they are related. So first of all, so let's recall, this is the same slide as before, almost. So any simple curve, so this would be our reference curve, we can encode into this driving function, which is just the image of the tip in this Loewner evolution. So some continuous function on the real line. And that function has Dirichlet energy, so it might be infinity. I'm not specifying the regularity here, so you want maybe absolutely continuous so that the derivative exists, but it might still be infinity. Yilin introduced this in her thesis and also studied a lot, when this is finite, and found that it's finite if and only if certain properties are satisfied, which somehow in the case of curves, can be seen as some Weil-Peterson type property, but that's a bit of a long story for here. Anyway, I defined that it might be infinity, just be with the energy of this driving function, which is the evolution of the tip on the real line in this picture. I call it I eta, because it's also the property of the curve, right? So that is the Loewner energy of the curve. And now you want to do it for many curves as well. So notice that it's at least non-negative always. Also, it's lower semi-continuous in a certain topology. Sorry. And has nice properties. So it's a good rate function. So then here is a little bit about many curves, because this one curve energy, so it's here, it's not maybe the most intrinsic thing, because you need to use all this Loewner evolution. Of course, it's a natural thing because it's the Loewner energy of the driver. But if you have many curves, you should have some kind of drivers for all of them, and it's not so clear how to use this idea to define this energy functional for them. And also it's quite unsymmetric because you have to decide where you start growing, for example. Whereas this theorem is only stating about some properties of sets in Hausdorff distance. So somehow we don't really want to have some time parameterized objects like that. What we can do for several curves. So let's say we understand this one. It also has other equivalent characterizations proven by Yilin. For several curves, which are supposed to be the classical limit of multiple SLE, there should be some interaction term. So not only sum up all the individual ones, which is here, that would be for independent, large deviation principle for independent SLEs. But there's interaction term. I don't have time to write it down, but you can express it as in terms of Brownian loops, essentially measure of all Brownian loops which touch at least two of the curves. And then there's a factor included in this potential functional, which is only a function of the mark points. So here is maybe xaj and bj. And what is here comes the Poisson excursion column between the points. So you might think this is maybe a redundant term, which is true for this theorem, but it's actually has some interesting properties in other aspects. So we included it here and we call this potential. And we define the energy then as the potential minus the minimum times some constant, which doesn't really matter. So then the energy, it's functional on families of curves, which is somehow given by the individual energies plus some interaction. And these things cancel in here. Okay. And then once again, so if you want to understand the large deviation, so let's fix some. So we look at this infimums over all eta in some set. So eta would be these kind of smooth looking curves. We would have our SLE curve, somehow the small kappa fluctuating near that. And then we want to measure what kind of closeness we mean, something like that. And this functional I describes this large deviation as a rate function. And it's almost the same as the potential H, but there's some, small difference. And I'm promoting the potential here because it seemed to be actually more natural in some ways. So this is why we focus on this. And So if you don't know about Brownian loop measure, and if you got lost a little bit with this definition of the Dirichlet energy, I will show you another formula for this, which is this more geometrically intuitive. Okay, I think I maybe, how many minutes I have left, by the way?
Wait, like 10?
Ah, okay.
Five or 10.
Okay, great. So plenty of time. So yeah, so I will show you another way to write this guy, which is maybe a little bit more intuitive. Here it is. Maybe let me reveal again. Yeah, so remember that this H, which is the potential, it's essentially the same as the energy, but there's some additional term, which is also keeping the information of the marked points somehow more specifically. So then we focus on that, and we get everything about the energy also from here. So here's one way to write it, assuming certain regularity, because what I want to do, so I want to take the Laplacian in my simply connected domain. So let's say the boundary is nice enough so that everything works, like the unit circle. So unit disk with the unit circle as the boundary. So I can take the Dirichlet Laplacian, so zero boundary condition. I can define its determinant after zeta-regularization. And okay, there are logarithms everywhere appearing. And okay, so that is some quantity which is finite and appears actually a lot in mathematical physics. But this is just a kind of global factor, it's just the domain. But now I have this multichord which needs to somehow affect. So then what I do, I subtract all the corresponding terms in the different components of the complements of the multichord. So they have different colors here. So C is one component, maybe this one. And I take the Dirichlet determinant Laplacians there. And after I do this, I end up with a quantity which is somehow measuring potential of these chords. So the dependence on eta is actually hidden here. And there's some universal constant that comes from the construction, but doesn't matter much. And hopefully it's now correct. You can calculate it. Right, so this is, this to me quite more intuitive once you see it at least. So okay, of course the potential of these chords should be, because they are somehow canonical and come from large deviations of Brownian motion. So maybe it's not surprising that the potential is measured by the Laplacians in these different components. And that is indeed the case when you have sufficient regularity. So notice that, for example, in this component C, maybe that one, so that is a domain which has some corner singularities on its boundary, which cause slight problems for the story. And we actually used something quite recent by these people to prove this theorem. So we essentially, so this guy on the left-hand side, it had the formula in the last slide, which was the definition. And now I'm claiming that the right-hand side equals that. And in a very vague sense, maybe you could say that both sides have the same kind of conformal restriction property, and then you can identify them in some special case. And that's how you get their equality. Very, very much simplified. I should have, it is here. So Yilin already discovered something like that. For the loop energy that I'm not talking about here, which concerns, loops on the Riemann sphere. And there you also have the loop is splitting the sphere into two components. And you can observe this kind of formula also for the loop energy, which motivated actually this theorem. So we kind of would like to define our potential in this way, but this is slightly weaker because we need some smoothness. So we define it instead in this other way, and we show that this is an alternative equality for it. And now if you think about this formula, nothing is really forbidding to go to some, other kind of surfaces and try to define this potential of curves in this similar way. So somehow this is much more intrinsic. And for the energy itself, it would be less clear because this one also encoded these Poisson kernels between the points. So that's one reason that this potential is actually a little bit more maybe intrinsic than the rate function itself. All right, so then maybe a little bit, few more minutes. I want to mention about the minimizers. So now one might wonder then, what are these optimal curves where the concentration happens? And that's where you find some fun connections to other things. So, okay, very briefly. The optimal curves are minimizers of the energy or the potential. So this is equivalent. So just talk about potential. So we call them geodesic multichords. So it's easy to see that if you look at the minimizer, it has this kind of symmetric property that each curve, this picture is actually bad, it should be more rigid. Each curve is just the hyperbolic geodesic in the component bounded by the other curves. So we call it the geodesic multichord by just having some name. So then we want to analyze those things. And because the rate function is good, some technical result, there exists some minimizers. And then you could ask how many there are. Of course, you would want to have a unique one, right? And so there's not quite a unique one because you need to fix how the curves connect, which I kind of did in the beginning. But if you paid a lot of attention, there was actually a Catalan number of options how the curves connect the points pairwise. And for each option, there will be one minimizer. And then we wanted to show that, okay, these are all minimizers. And it wasn't so easy than we thought. And here's a maybe recap kind of theorem, which is quite informal written about this. So how did we then find? So the middle thing is maybe the main point. So there's a unique minimizer for the potential for each pattern alpha. So alpha is the connection pattern. And how to do it? So if we have a minimizer, so that's a geodesic multichord, we can construct actually, if we go to the upper half plane, there's a picture in the next slide. We can construct a rational function with certain critical points, which are kind of given by the mark points, but they are in the real line if I'm in the upper half plane. And then what we want to do is to classify those rational functions. And that was partially done by Goldberg. And that's what we used to show that actually for each pattern, there's exactly one such object. So in total, there's this Catalan number of them. And that accidentally was related to some problem in enumerative geometry, in real enumerative geometry. So that was kind of a little bit surprising to us. So if I have maybe 2 more minutes, I will show 2 more slides maybe. So, okay, let's go to the upper half plane. So here's our geodesic multichord. And now, because I'm in the upper half plane, I can reflect. So I can look at the complex conjugate one, just like that. And now I have this kind of chords on the Riemann sphere. And I can do the following. So let's pick one component, like the yellow one here, in the complement of the chords. And let's map that conformally to the upper half plane. That I can always do. So now, by the geodesic property, I can do a reflection along one of these chords and map this component to the lower half plane. So that chord will be mapped somewhere. And now I can keep reflecting. And in the end, what I find is a covering of the Riemann sphere by itself. So that is a rational map, which is ramified at these points. So you see that, you know, there's a critical point of index 2. But by this construction, so you start from a geodesic multichord, which is a minimizer of the potential. You construct a rational function, which has these critical points, which are the mark points. Those are index 2. So we actually know the degree also. And that was the first bullet in the proposition. It's kind of cute when you think about geometrically. And I think I should stop so I get back here. Just mentioned, so that was the bullet. And then you kind of classify those. And in the process, you end up proving something like that, which was fun. But it's a special case only for some more general conjecture. Here's some literature about that. But yeah, I think I should stop because it's more than past.
Thank you.
So any questions?
Questions? Yes. There's one in the chat that wasn't answered, I think. Or if someone wants to go ahead first. Okay, I'll just ask this one. So in your energy potential, why was it the Dirichlet Laplacian in the subdomains?
Why Dirichlet? Right. So I guess the other option would be Neumann, where you have some reflection in there. I don't know. I think it's just comes up naturally for this construction.
Is it related to what you have on the previous slide? I think it's really easy to see the relation with the
For the oops.
Yeah, the M, like the Brownian loop measure and these
Yeah, I was also thinking that. So the Brownian loop measure is this is the measure of all Brownian loops which touch at least 2 of the curves. And okay, I guess one way to see it is that, so there's this Brownian loop measure term, indeed, which is somehow this finite, because it has loops like that. Then there are these other terms, which you can somehow think about as Brownian loops, maybe touching just one curve, but this would be infinite, because you know there are these tiny loops. So you want to somehow get rid of that. And yeah, so in this determinant formula, so there's actually, I should have put here by Morris and Sheffield and other people. So they have quite recent preprint about this Laplacian determinants. I think they have connection to Brownian loop measure. We also wrote one result about that. Somehow essentially saying that, okay, this would be like the total mass of all Brownian loops in the domain, but that's infinite. And then you would subtract somehow all these components, and you would somehow cancel out all the small loops because, of this. And you would be left with somehow, the loops which are macroscopic, and they would be finite. And I guess somehow the interpretation of this as the total mass of Brownian loop measure. So there you have somehow this Dirichlet boundary condition. Yeah, it is the natural one to consider. So they are killed when they hit the boundary, something like that. But I don't have a philosophical reason actually. Maybe Yilin has if she's there.
She wrote something in the chat. But...
Yeah, I was answering to the question in the chat.
Okay, great.
Yeah, I have nothing to add.
Yeah, okay. Right.
Are there more?
That's a good question.
I have another question, if possible.
Okay. Go ahead.
This is somewhat orthogonal to what you've discussed, but have you, or do you have knowledge of the conservative versions of these systems? So the Ising spin system is a sort of spin flip thermodynamic system, but there's also the conservative version, Kawasaki dynamics, which conserves the phase fraction of spin up and spin down. So I was wondering what's known for those systems.
But so that would be really in the easy model, right?
Yeah.
Okay. So then you would put dynamics on this configuration. But so what is your question?
So again, in that setting, there's a conservative feature where the phase fraction of the spin up and spin down is conserved as you explore the state space. So here it looks like you've got in the Ising system here, it looks like a critical state where it's 50-50. But in the conserved system, you can have minority phases in a sea of the majority phase. So just again, what's known about the critical behavior, either analytically or with renormalization group in that case, if you knew?
I don't think I know. I can give an answer to that.
Okay, yeah. Thanks. Out of curiosity.
Yeah, thanks. I'll look it up.
More questions? Okay, so I guess let's thank Eveliina again for the great talk.
So my video is